This is a short little video that helps you understand why the pH is not always 7 at the equivalence point. And this might help to address some of the questions that might come to mind as you read through your lab for this week, because you're doing titrations. So the basic titration that you'll recall from your high school chemistry or previous chemistry experience is the reaction between a strong base and a strong acid. So we will use, we've written out here the very common examples of each: sodium hydroxide reacting with the strong acid, hydrogen chloride, or hydrochloric acid. And like in any titration, neutralization reaction, we have the formation of the salt. And so here we have it, sodium chloride. And so to balance it out, we see that water is formed. So the equivalence point, by definition, is the point in the titration where you've got stoichiometric amounts of your two reagents. So basically you've got equal numbers of moles of your strong base and your strong acid. And of course, if that's the case, and this is completely ionized in solution, then then that means that you have equal number of moles of your hydroxide ion and your H+ ion. Okay, because sodium hydroxide will be completely dissociated or ionized, and so will the HCl. So equal number of moles react to produce that number of moles of water. And so essentially, at the equivalence point in this titration, you do not have any excess OH- or any excess H+, and so therefore, with their concentrations being the same, we have our pH of pure water, 7. Okay, so that seems to make sense. So let's take our next example, which is the titration of a weak base with a strong acid. And the weak base that we're showing here is ammonia, NH3. So let's react in a titration the weak base ammonia with hydrochloric acid, our strong acid. And again, we have their salt formation. We've done this one in class, NH4Cl. At the equivalence point, you are reacting, you have stoichiometric amounts of your weak base and your strong acid in solution. So how will they react? Well, they're going to form, as we just said, NH4Cl. But we recognize that the ammonium chloride is, of course, present as an aqueous ammonium chloride in solution. So it's completely dissociated, completely ionized. And Cl- in solution doesn't behave as an acid or a base. But when I have NH4+ in solution, it actually behaves as an acid, making water, therefore, its base to react with. And so when NH4+ is in water, like we have here, it forms a little equilibrium between it and the water. And what we have on the other side produced is ammonia plus H3O+. So we see that at the equivalence point, so when I have equal numbers of moles of my weak base and strong acid, because of the way all the species in the water react with each other in an acid-base fashion, we are actually left with an excess of H3O+ that's formed. And so the pH at the equivalence point is a little bit acidic, or less than 7. And this will always be the case when you react a weak base into strong acid. All right? So weak base plus strong acid, you're at your equivalence point. So even though you're reacting equal numbers of moles of your weak base and your strong acid, you end up with excess H3O+, and that's because of this. And any weak base is going to do the same thing, and you'll have a little bit of H+ or H3O+ produced in excess, making it a little bit acidic. So we've done strong base, strong acid, and now we've just looked at weak base, strong acid. So the last consideration is a strong base with a weak acid. And so let's look at that. And what is the pH at the equivalence point? Let's take sodium hydroxide as our strong base, and our weak acid we will use acetic acid. And at the equivalence point I have equal number of moles of my strong base and weak acid that I react together, and I get the formation of the salt on the other side. And I know that the salt is aqueous, and so it's completely ionized or dissociated in solution and actually exists as Na+, the sodium ion Na+, and the acetate ion CH3COO-, each in solution. And do either of those act in an acid-base fashion? Yeah, in fact the acetate ion can react with water as to produce some OH- on the other side. So my pH at the equivalence point is in fact not 7 for this titration either. So when I react a strong base with a weak acid, when one of them is weak, my pH at the end point is not 7. At the equivalence point. I want to be careful with that nomenclature. So in this case, where I have a strong base and a weak acid, the pH is slightly more than 7. It's slightly alkaline, slightly basic. And that's because when these two things react, even in stoichiometric amounts 1:1, I do get, in addition to these products, I do get a little bit of the OH- forming. Okay, so these equilibrium arrows, as I said in lecture, they will be parts of equations that we will take a very close look at second semester in General Chemistry 2. We just need to know that these conditions exist for now, but we'll look at them quantitatively in second semester. So just to recap, finally, when we have a titration between a strong base and a strong acid, react stoichiometric amounts to reach the equivalence point, the pH will be 7. The salt that's produced, sodium chloride, neither of its solvated ions behave in an acid or base fashion with the water. Excuse me. Next case, a weak base in a strong acid. Using an example of ammonia and HCl, we have the formation of the salt. It is completely ionized or dissociated in water, and we know that NH4+ does behave in an acid-base way with water. Specifically, NH4+ is an acid. It donates one of its protons to water, forming NH3 and H3O+. So at the equivalence point, the solution is slightly acidic. Weak base, strong acid titration, the equivalence point is slightly less than 7. Why, it can be more than slightly less than 7. It depends on the acid and base pair that you use. And finally, in the titration of a strong base and a weak acid, the pH at the equivalence point is slightly basic because of the production of the hydroxide ion. Okay, so in this case, I'm using NaOH and CH3COOH, and I get my salt produced like I do in any neutralization reaction, sodium acetate in this case. It is written as aqueous, so it's completely dissociated or ionized in solution, and exists as Na+ and CH3COO-. The Na+ ion doesn't behave in an acid or base fashion with water, but the acetate ion, CH3COO-, does, again, in a way that's explored in detail in second semester. It's called equilibrium, and it reacts with water as a proton acceptor, and takes a proton from H2O, leaving behind the OH-. So pH is slightly greater than 7. So as you read through this week's lab and the pre-lab questions, you'll see descriptions of a situation where the pH at the equivalence point is not 7. So I wanted to point out these 3 different kinds of titration scenarios and hopefully shed some light on why the pH is not always equal to 7 at the equivalence point, because I think that most of your pre-university experience with titrations are with strong acid, strong base titrations. So we're just exploring 2 other scenarios to add to that one. Anyway, that's it, folks.